look back all the way to the surface of edge of opaqueness and map it out. And so these famous microwave background maps that you, hopefully most of you have seen, are actually you go up in the with a satellite or with some tool in some kind of radio telescope on Earth, and you really look all the way back to the edge of opaqueness of the universe. And so this and many other things, you model the formation of nuclei, as I think I mentioned briefly earlier this week. There's a long list of things that you study. You basically translate known physics into the context of the Big Bang, and it all hangs together very well. You do have to add dark matter. You have to add dark energy. Those are things we don't understand very well. But there's a lot. So there's a mixture. There's a few things we don't understand very well and lots of things we seem to, and it hangs together pretty well. Was that a hand up for a question?
From the drawing, it looks like it really was a phase transition, like from opaque to
yeah.
Right? But if I just take anything and I dilute it continuously, then it will not get transparent with a phase transition like behavior, right? So
yeah, it's not. I don't think it's fair to call it a phase transition. But this is sort of logarithmic scale. So on a logarithmic scale, any transition looks abrupt, and that's probably the thing. So the scale, there's a particular time scale where a particular temperature, particular time scale where the transition is happening, and then after that, you care about longer time scales. And so that one looks short.
So the general shape of this thing looks like the universe is aimed at collapsing again, but that's just because you've got a logarithmic time scale.
So one thing you can tell is that this was not produced by a physicist. It was produced by an artist, and I think with a few exceptions, getting a PhD in physics selects against being able to do things like this. but yeah, I don't know. Don't take that shape seriously. I'm going to show you more stuff to interpret that. Okay. So and then so this, when you see plots like this, it's a quantification of these kinds of images. Okay. Now I want to say a few things about curvature. This may be the actual plot that Henry borrowed, or one like it. No, it's not exactly the one you borrowed, is it? Okay, so now I'm trying to. So the generic thing that happens when you get taught inflation is you get taught all the cosmological problems, and then you get taught how inflation solves them. And what I prefer to do is be very careful about this and call the problems first of all features, and then tell you how you need to think if you want to call them problems. And there's an extra piece that comes if you want to call them a problem, but it's certainly a feature, and so let me tell you what it is. So we're thinking of curvature like a density, and you can say, well, suppose it's just you throw in some curvature of equal density to the total, some significant fraction of the total density of the universe at early times, and what you find is that because it dilutes more slowly than other things, you predict that the universe is dominated by curvature today. And as far as we know from data, there's no evidence of curvature at all. So, and remember, this is a logarithmic plot, so this is a massive deviation from observations. You can say, okay, well, let's bring this down by orders of magnitude, but no dice. Basically, because I'm choosing this to set this up a long time ago, and it scales differently. And so what you have to do is actually bring it way down to get it consistent with data
today.
today.
It's zero, can you?
Well, that's one thing you can do. Not on a log plot, but
Well,
but
completely get rid of it.
yeah, right. So then you can worry about this, and well, I shouldn't say worry. So I'm already sort of catastrophizing this a bit by putting a symbol like that there. But it's a feature. You have to make the curvature small, maybe 0, to in the early times to be consistent with beta. And did I see another hand? No. Okay. So I'm going to actually. So what I've done is I've put in sort of slides showing the equations that go with the pictures, and they're there in case we want to get into that. But I'm going to try first round. I'm just trying to skip and do some of these things with pictures, and you can slow me down. So sorry, it's annoying to flip through slides, but that's what I'm going to try to do. There's another thing, gravitational instability, which is just saying that so we're starting with a homogeneous isotropic universe, but gravity tries to clump things up. And so I think I mentioned already on Monday, this is a sense in which the universe is highly out of equilibrium at the beginning. It's a good fit to data, so that's great to model it that way. But the fact is that gravity will try to clump things up. There's something called the Jeans length that sort of controls what point that happens. And but the upshot is that we have to assume that that the universe is very smooth on scales where it might have been clumping. So to fit the data, there's I don't want to dwell on exactly how I phrase it here on the slide actually, but basically there's another. Oh, here's a nice. So one thing you can say is, what's the most unsmooth thing you can have? You can put all the matter in the universe into a black hole. That's like the culmination of full gravitational collapse, and the black hole has an entropy, and you can compare that with the entropy, the sort of known entropy of the universe, which is actually mostly black holes. Well, I guess I'm doing this for the early universe, so it's just the entropy of the particles in the universe, and they're different by 35 orders of magnitude, and that gives you some quantitative measure of how homogeneous the universe is compared with how it might be clumped. Yeah.
This is being in entropy, it's already an exponential, and this is 10 to the 35th of that.
You can right. You can put it that way. Yeah.
So you don't need an initial clumpiness in order to get structure today, right? That you can.
Yeah. So what I'm saying is, well, we're going to get the structure today, but what I'm saying is there's not a lot of it even today.
I understand,
Yeah.
but our observations of non-zero clumpiness today are still consistent with exactly zero clumpiness in the distant past.
I'm not going to. I'd rather try to answer that a little bit later, because in the end, no, there has to be some. I'll just say there has to be some seeds of the clumpiness, but very little. So the seeds of the clumpiness we see today are the standard picture now is you'd start with a variability in the density of 1 part in 10 to the 5. So very, very subtle variations. That's smoother. When I gave my TEDx talk, I worked out I had a piece of glass that was very smooth, and that was, 1,000 times smoother than a piece of glass at 10 to the 5.
Then this is different than the curvature thing you just talked about a second ago, because that could have started at exactly 0.
Yeah, that's a good point.
Okay.
Yeah, so we have evidence that right. So you could. Oh, geez. I mean, yeah. So I think if you pose the question, what about perfect homogeneity, you'd have to deal with quantum fluctuations one way or another, and I'm not convinced. I'm not sure where that would. Let's talk offline. What would it mean to say a perfectly homogeneous universe? My guess is that the symmetry would break by gravitational collapse.
That's the question.
And
observations are because what I want to say is that in the same way that we postulate very low entropy initial conditions just to have an arrow of time in general classical mechanics, to what extent can we do that here, or to what extent is there just some small but non-zero parameter that requires explaining? I understand that there's like several of these things interact.
So I like when I talk about inflation, and see now we're slipping into priors already, which I'm trying to avoid. So I told it. So Adam, I told everyone that your job is to call me on my bullshit as we go, and you're well. Sorry.
So okay, Jess, in answer to the question, I think a party line is that, according to the standard model of inflation, is that every piece of structure you see in the universe, including planets and galaxies and you and everything else, all the deviations from non-uniformity started out as quantum fluctuations very
So,
close to the Big Bang.
that-
So in fact,
But-
there's no need to posit any classical inhomogeneity in the early universe. As far as we,
Is that
according
true
to the standard model,
with inflation or?
with-
So we're doing Big Bang. So we're not doing inflation yet. So,
Okay.
Yeah, so without inflation, you require.
so I'll call you on your bullshit.
In fact, that's the famous Harrison-Zolovich spectrum. So in order to explain the structure of galaxies that we see, people before knowing anything about inflation posited that there had to be a seed spectrum whose origin they don't know.
Right.
And there had to have no scale.
Well, so that
posit
I would say, so we can talk about, they didn't say very much about scale invariance. Actually, if you look at the papers, I can show you quotes. They actually are very, very vague about the scaling of it. But,
Yeah.
that's more history than. So right now I'm just talking about the Big Bang. So I'm trying to introduce the Big Bang, and then we're going to add inflation. So yeah, you need some seeds, and in whether they're yeah.
But we don't need curvature seeds.
Well, because yeah, I suppose you could ask what kind of So we'd be happy to not have curvature seeds. In fact, inflation predicts curvature is one thing in an FRW metric, and it's another thing in terms of what you observe. And by the observational standard, inflation seeds some curvature as well.
Can I just add
Yeah.
one thing? I think an issue trying to do just like the curvature presented earlier, it's treated as like constant. So it would be just constant spatial curvature. So it's already sort of assuming homogeneity when you describe it in that way. So it wouldn't be able to see the structure formation properly. You'd have to put something.
It's a separate thing
Yeah.
in that context.
Right, but so in this case, the curvature and the density perturbations are two separate ideas. One of them, exact zeroness, is consistent with observations, and the other one is not without something like inflation.
I think I left. So I tried to call the slides. One of my slides actually says it's a similar kind of thing. The curvature and both are instabilities. So the curvature and the gravitational collapse are instabilities. Very similar feeling.
They seem importantly different to me.
There is a sport out there that tries to explain away what we view as a cosmological constant by living in a locally underdense bubble. Right? And the problem with GR, unlike any other theories, is non-linear. So it's not clear when you try to write down a solution that's some homogeneous solution plus fluctuations, whether you're doing averaging correctly.
Okay.
So there
How much
are
time do I
people that actually postulate, like, maybe we live in a locally
Are we going to 11? I mean, to.
different.
Is it 2 hours?
Further away.
Okay.
But that's sport, but then you have to also fine tune, your locations in that bubble to explain.
Okay, so I have 45 minutes. So I'm going to call. Okay, I've just checked in how much time I have. That's a good conversation for later. But I have more stuff I want to get to in the tutorial. So monopoles. Actually, I would say the monopole problem really is like the most real thing. It's the thing inflation does for you that's least subject to all these arguments about priors and what it means to explain something or other. You can ask the question, so it could be monopoles, it could be anything. So we have this nice picture of the universe, and many of the successes are based on the fact that it's dominated by relativistic matter at early times. But you could find yourself in a situation where your theory predicts that there's actually a bunch of non-relativistic matter that shows up very early in the history of the universe, such as magnetic monopoles. And this was, a lot of people here have deep respect for John Preskill. He first splashed onto the scene by basically showing the particle physicists that all their favorite ways of thinking about grand unification led to a cosmological disaster because they introduced non-relativistic matter in the form of defects from phase transitions at early times, which then came to dominate the universe. So actually, these theories that predicted magnetic monopoles. So now the party line is that no one's ever seen a monopole. Back then, we thought someone had seen one. but the prediction of all grand unified theories of that era was that the universe would be made entirely of magnetic monopoles today. So that was this radical. So you didn't have to wait for someone to build a satellite and go up and measure subtle fluctuations in the universe. You knew right off the bat that he'd basically ruled out all grand unified theories just like that without collecting any additional data. And so that was this huge drama. So this was a crisis for the particle theorists. In many ways, it's what woke particle theorists up to the fact that they actually have to pay attention to cosmology to do particle physics. And then, so it was very exciting that inflation's going to address this, which I'll show you in a bit. So this is a disaster. So it really earns its little yellow construction zone.
What are the two blue lines?
So this is this blue line is the normal amount of non-relativistic matter that we need to understand what the universe is like. And this is non-relativistic matter that could appear in certain theories, and if it does, it destroys your cosmology.
Just because relativistic matter means stuff that has zero mass, or